Okay, well, let's go ahead and get started. I'd like to welcome Jack Conrad, who's applied to join us as an associate research scientist. He was recently a postdoc at Marshall Space Flight Center, and he's now hanging up in the DC area, knows people at Goddard and Maryland and other places, studies the weird surface features and looking for insights into interior processes on rocky bodies and icy bodies throughout the whole the solar system. Welcome, Jack, and I'll turn it over to you.
Thank you very much, Mark. Let me start sharing my screen. Just do it this way, a little bit easier. And then start the PowerPoint. Wonderful. Awesome. Just real quick, Jack, is everything coming in great?
Yep.
Awesome. Let me adjust that. Great. Well, thank you very much, Mark. Right. So as Mark was talking about, I'm somewhere in terms of planetary science research. I'm somewhere between a geologist, geomorphologist, and a geophysicist. However, if you go and talk to any one of those individual people who really know that they're one of those types of folks, the stuff I do really doesn't sound like I do what they do. So I just sit sort of right in the middle, which I find to be very scientifically fulfilling, as I can sort of reach my hand out and work on a bunch of different types of projects. Before I talk about all these different types of projects, I thought I would talk a bit about myself and my planetary science journey. And I'm going to talk about it through the means that I actually went about discovering it. So I first actually learned about planetary science as its own field at Purdue University up here in West Lafayette, Indiana. It was there I was lucky to meet Professor Jay Balash, rest in peace, during my sophomore year. He and I worked on a project involving the acoustic fluidization process. While I've moved on from that project, I never published anything with it. It sort of drove an interest in the very unique, very underexplored landforms throughout the solar system that are really kind of rare on Earth, that are common elsewhere. After getting my bachelor's in physics at Purdue, I went out west to Santa Cruz, California, home of the banana slugs. There I worked primarily with Professor Francis Nimmo. We worked on a wide variety of different projects. However, I went out there in the summer of 2015, and those of you who might remember what else happened that year, that was July was the flyby date for the New Horizons probe. So we got our first really great images of Pluto and started to understand it was a very weird, possibly tectonically active world. And so studying Pluto and its largest moon, Charon, formed the bulk of my PhD research. And unfortunately, I won't be talking about it much today, but I will be talking a little bit about some other projects I did while I was a PhD student, specifically looking at lunar gravity and lunar thermal history. After I got my PhD in the fall of 2020, I made the decision to accept a postdoc at the NASA Marshall Space Flight Center right in the middle of the pandemic. I still think I made the right decision, although it was a very harrowing journey to take, and a little bit isolating, I'll say, but I think we were all pretty isolated back then. For those of you who might not know, the NASA Marshall Space Flight Center is in Huntsville, Alabama, also known as Rocket City, USA. Is the home of the U.S. Space and Rocket Center and Space Camp, and it's very fun living in that town in terms of a person who's really interested in space, because you look around and you see the Saturn, the Saturn V rocket, and you use that to orient yourself around town. You don't really need a map as long as you know where that is. But while I was there, I worked primarily with Dr. Caleb Fassett, who is actually now at APL. But there we worked on looking at impact craters from small to large, for over a variety of different ways, mainly through the methodology of crater counting, but we were looking at both the actual process of the impact cratering itself, as well as using it to date and age surfaces. I also worked a lot on a lot of lunar brills and other strange, I guess maybe not super strange for those of you who look at them a lot, but sort of unusual channel features in the context of Earth. There's a lot of channels out there that weren't formed by tectonics or water. And they seem to have formed through lava flows that could erode. That's still up for debate. They could also be constructional features that have collapsed. And so I've done a bit of work looking at those, and I'm hoping to propose something based off of that. After I wrapped up my postdoc, I decided I didn't want to be in I didn't want to continue a three-year long-term relationship with my partner. So I went up to join her in the Maryland side of the DC area. We live a little bit south of College Park. She is currently a postdoc at NASA Goddard, working with the MAG group. And the upsides of living with her are great, but I also get to live with our cat again. This is Sarek, who may or may not hear my voice and think I'm doing something interesting and come and visit. But he probably won't. He's pretty sleepy right now. Bonus points out there if you know what sci-fi franchise his name is from. Right. So that's where I went around the United States. But where have I gone around in terms of worlds in the solar system? I've looked at a whole bunch of different worlds. Basically, if it has a solid surface and no atmosphere, I've probably thought about it. But these are the 7 worlds I have thought a lot about and have either published conference articles or papers about. And I mean, I think the only one that people might not recognize right off the bat is right here. This is Sharon. It's, I think, my favorite on this list. I have my research into it has shown that the little moon likely had such high ocean pressurization as it was freezing out very rapidly that it literally cracked itself in half. At least that's what the topography is saying when you look at the surface. Speaking of topography and how I look at things, my research, beyond looking at a whole bunch of worlds, is broadly separated into 2 different, methodologies or sorts of the things I look at. The first half is I look at impact craterings. Impact cratering, I started my initial planetary science work with Jay, and I don't want to leave any of that behind. And with Francis, I sort of started developing a lot of techniques that look at the topography of worlds and relate that topography and morphology of very specific features to the internal structure of these worlds. Part of what I hope to do at PSI is to both add more worlds to these ovals, maybe make some new ovals, as well as grow those ovals and sort of figure out if I can apply some topography analysis to Europa, say, in ahead of the upcoming Europa Clipper mission. All right. So after that sort of coldish open, let's call it lukewarm open, I thought I'd finally give a talk outline. So we've already talked about myself, so I'll go and cross it off. The next 3 parts of this talk are really 1 really big part and 2 kind of short parts. The really big part is the next one where I talk about geologic contrast through secondary craters. Then I can hopefully we'll have enough time so I can talk about work I've done about large impact structures on the moon and how that's related to the thermal history of the moon. And then wrap it up with talking about channel features on Venus and the moon, talking about canali and brills respectively. But first, the geologic contrast through secondary craters. So in general, why do we need to use indirect methods like impact craters to understand the geology of a world. Well, beyond being the geology themselves, the actual methods that we can use to understand the surfaces and upper parts of the crust and mantle of worlds is very limited. Rovers and landers are very spatially constrained, even though they can dig through and understand those upper centimeters to meters. When we start looking at remote sensing, we can get a global view of the worlds. But spectroscopy is very limited to upper centimeters. And when you're looking at geodesy scale, you start to lose some of the fine structure. So really there's a lack of non-radar ways to measure sort of porosity and strength in the upper tens of meters to few kilometers. And this is where impact craters come in. We have a really good sense for how the size and the shape of an impact crater relates to various properties of the impactor and of the crust that it impacts into. If we get really good measurements about density or strength or porosity, we can start to say stuff about the impactor and vice versa. This has been done widely on the moon using GRAIL data to get at porosity. And when you look at really large impacts, you can start to cancel out or make assumptions about some of the impactor properties and crustal properties to help you get at the ones you can't make assumptions about. So that works really well for large impact structures and really helps you figure out sort of really broad strokes of the crust and the actual, the entirety of the crust itself. But if you want to get at the sort of finer detail parts of the crust with impact craters, we got to get a little bit more creative. And so, looking at individual impact structures, when we're looking at, tens of meters to hundreds of meters up to a kilometer size impact craters, gets a little bit rough. And so we have to use distributions of impact craters. However, when we are talking about impact crater distributions, size frequency distributions, 99 times out of 100, the study is going to be about trying to get at the differences in ages between different areas of the surface or different geologies. Sort of in this example here with the sort of cartoon that I've drawn, if you assume that all these craters are the same size, they're not for a reason I'll explain later. If you assume they're the same size, this area on the left has more craters than this area on the right. Thus, the area on the left is older, right? So most of the time when we think about measuring impact craters of small sizes, this is what we're getting at. However, if we have a situation where you have external evidence that the surface ages in these two areas are the same, and you go and you measure the actual crater distribution in these two areas, and you get a difference in their cratering distribution, what is causing that difference? And that is due to going back to those crustal properties, likely differences in strength and porosity. Because if the areas are the same age, and you're just sourcing impactors from outer space, the distributions of the actual impactor properties are going to be the equivalent between these two areas, and thus it's only the crustal properties, really, that those like strength and porosity, that can drive the difference we see. This actually really works great as a technique, as shown by Colin Dundas back in 2010, where if you can find the perfect area where you have two different areas that have the same age, two different geologic units, you can actually get at a qualitative and nearly a pretty good quantitative difference. However, that's going to be really rare. Especially since the way that we actually go and measure ages on surfaces is typically through craters, right? There's sort of a circular logic flaw to using this most places with primary craters. Can we still use impact craters to measure property differences somehow? And yes, we can. And that's only if we can find a source of impact craters where they all are from the same distribution of impact events and all form at roughly the same point in time. And you get that with secondary cratering. Secondary craters are craters formed by the ejecta of a primary impact event, where you have a crater impactor come in from outer space, hit the surface, blow up, throw a whole bunch of material out, and that rains back down onto the surface. A large amount of that mass is going to have a high enough velocity and high enough mass such that they form craters themselves. So we can find a situation like this, where we have a primary crater and a bunch of secondary craters on top of a geologic boundary. We can then go and measure up the secondary craters on either side of that boundary and see if there's a difference in diameter across the entire distribution of impact craters. And if we go and we measure that difference, then that difference is being caused by differences in the crustal properties, because across this cluster of secondary craters that hit this boundary, the actual distribution of ejecta should be pretty well mixed, and thus should represent a single distribution of impactor properties. And thus the actual differences are only being caused by strength and or porosity. Okay. This is just a concept. We should actually go and talk about a place that I have tested this out and shown it works. But if you want to go and try to find a place, you gotta go with the best possible situation and then go find the actual hard places to apply this. And the best possible situation for this method is a world with good imagery, large, young primary craters. So you need a world that resets its surface, relatively a good bit, but not too much. Clustered secondary fields, which you get from almost any primary crater. Clear geologic boundaries and a lot of geologic boundaries. And you want secondary fields that cross those boundaries. And the only world that really meets all these qualifications in multiple different locations that Caleb and I have found so far is Mars. And so I'm going to talk about our best situation, or our sort of primary first focus study location on Mars, which is around Tooting Crater. So this is one way to go through this process. This isn't the way I'm actually going to recommend people do this if they want to go about, try to apply this method themselves. But step one, you find a large, young primary crater. Tooting Crater is large. It's about 27.2 kilometers in diameter, which is about the same, depending on which length scale you're measuring as the District of Columbia. I currently am living in the scoop out part of this rampart right here. I'm trying really hard to hold my breath because air on Mars is pretty thin. But Tooting is also very young. You can see that in the details on the ramparts themselves. That is this very thick ejecta, although there's plenty of secondary impact craters around it, and a lot of these small craters around here that you might be able to see depending on the resolution of your screen are secondary impacts. Get a little drink of water while you all look at the wonderful image. Right. So we know Tooting Crater is very young because there's very few primary craters coming in from outer space on top of the thick rampart ejecta. Right, so it's sort of the best possible primary crater for us to look at. If it's large, it's going to produce a lot of secondaries. So let's go and look for those secondaries. But first, we need to identify where the geologic boundaries nearby are. In Amazon, so Tooting impacted into Amazonas Planitia, which is this large, wide, very flat volcanic plain. And it's located right next to the Olympus Mons Oriole. I apologize if I pronounce that 5 different ways. But this Oriole is a landslide deposit, a rather old landslide deposit compared to the volcanic plains next to it. That actually came off of the flank of Olympus Mons as Olympus Mons was growing. So we're looking at a very loose, very weathered, old landslide deposit next to and being covered up partially by volcanic plains to the left. So we scan along that boundary to try to find secondary crater clusters. When you go about doing this, if any of you out there want to go about doing this method yourself, I would actually do it in the opposite order. Say you're looking at a location that happens to have a geologic boundary and you see a cluster of secondary craters that crosses it. Then you go back and trace out where the primary crater is from there, and then continue doing all this, all the work here. But in this case, we start from the primary, we look along this boundary until we find a really good cluster of secondaries, which we find here, about 165 kilometers away from Tooting. I'll keep the Amazonas Planitia, which I'm going to start calling AP, and the Olympus Mons Oriole, which I'm going to start calling OM, sort of to the right and to the left and to the right, respectively. And you can see here, I'm going to go ahead and put a circle around it, the cluster that we found of secondary craters. This is a pretty big cluster of secondary craters. They're usually not this large, and you can actually start to see some of the internal variation within the cluster. But hopefully by counting enough craters on either side of the actual boundary, we can start to get at the difference in the crater sizes, which I will show by going up close. This is a much closer view of that previous image, and I'll throw up a rough boundary separator here. And you can see that the secondary craters on the left side in the Amazonas Planitia are larger than those in the Olympus Mons Oriole, at least from the first look at this image, right? This is just with your eyes. It's not, doing your due diligence and actually counting up craters on either side. So we go and do that. The areas we chose are here for this secondary crater cluster. The Amazonas Planitia here in blue, and the Olympus Mons here in a light yellow. We made sure to put a buffer between these two areas because the flows of the lava, or lava flows that created Amazonas Planitia, sort of butted up and flowed around the ridges of the Oriole and flowed in. So we want to make sure we avoid hitting pockets of what is actually Amazonas Planitia material, or really thin Amazonas Planitia material here. And so we're deep, pretty much as deep as we can go into the Olympus Mons Oriole while still being within the cluster of secondary craters here. And so from these counts, we get this data. This is a cumulative size frequency distribution plot. So the y-axis here is the number of craters per kilometer squared, so crater density. And even though I forgot to put it, it is of whatever meter or whatever diameter size you are and greater. So when you plot craters, your crater counts in this way, you're going to have a sort of decaying power law of impact crater densities. So as a result, you can see that not only are these two areas very different in size, or they have secondary craters very different in size. Looking at this, there's also some very weird sort of things happening within the size frequency distributions themselves. You can see that there's actually a roll off. Sort of if you trace out a straight line here, a roll off in the Amazonas Planitia that does not occur in the Olympus Mons Oriole. So the fact that there's a roll off happening one and not the other implies that it's not necessarily a counting issue. I would be typically cutting off a lot of the small end anyways, because even with high-res images, things get a little bit tricky trying to identify every single crater down to even 50 meters. But some of this roll-off could be due to actual geologic differences, becoming smaller between the two areas as your crater size gets smaller. You're sampling less deep into the crust. And then, large craters are stochastic, so we don't really look at those. But in the middle, you can see it's pretty consistently spaced out from each other, which is, I think, pretty interesting and shows that there's a consistent difference sort of across as you go through the depth of the crust in these two areas. Right. So how do we actually go and compare these two? Well, this can be pretty simple, but we literally take the Olympus Mons Oriole, the diameter of all the craters we measure, and we multiply them by a factor. compare them to the Amazonas Planitia, scale the cutoff that we used of 50 meters, and march that until we find our sort of best possible overlap, which occurs here. And you can see a couple things pretty clearly within at least our counting errors, which are these very thin gray bars that are kind of hard to see on your screen probably. These two distributions, when you multiply the Imspon's Oriole by the factor, you get that they have pretty much the same shape. They have very much the same slope, about -4 in the power law space. So slope of -4 in a log-log plot, right? And that is actually a very nice sign because secondary crater distributions are much more varied in this power law slope compared to primary source craters. And that they have they range from about -3 to -8, whereas primary craters range from about -2 to -3. And so we are looking at secondary craters here. They both have roughly the same slope. They both pretty much look the same when we overlap them, and they overlap well when we multiply the Imspon's Oriole by about 1.43. There is some error bars in that, of course. We use the two-sample Kolmogorov-Smirnov test and this is where it sort of passes the null hypothesis best. Yeah. Right. So not only do we know that, and we can confirm what we saw, that the Amazonas Planitia has larger craters. They're about 43% larger across that distribution compared to the craters in the Imspon's Oriole. And so in terms of the actual geology difference here, that means the Amazonas Planitia is either lower in strength or lower in porosity. As you form an impact crater, you have to crush out the pore space, break up the rock, and then fling it out, right? And that's going to be easier to do when you have less pore space to crush out or your rocks are weaker. So those of you out in the audience might have a good guess for which of the two parameters here, strength or porosity, is the likely controller in this situation. Typically one of these dominates, whether we're in a more strength dominated regime or a more gravity dominated regime, or depending on the actual geology in play. Just looking at the geology here, those of you out there might have a good guess. So keep that in your brain as we actually go and look further than just the qualitative difference here to an actual quantitative difference. How do we translate that 1.43 into actual numbers? And so we do it using the pi group scaling equations for impact craters. I'm not going to show this up on the screen because they are notoriously complicated, but basically by taking two sets of equations, one for the Amazonas Planitia and one for the Imspon's Oriole, we can divide one by each other and set those equal to the actual crater ratio factor that we found, and some other terms. So using those and sort of assuming that one of these is equivalent across this boundary, we can look at the sort of variance we expect in the other property. So when we set porosity, equivalent between the two areas and at a reasonable, like 15% value, and we vary the effective strength in the Amazonas Planitia from about 0.1 to 1 megapascal, which is a reasonable range for pretty loose to pretty cohesive rock, sort of right in the middle. We get that the Imspon's Oriole needs to be about 3 to 10 megapascals. I say about and kind of at the same time because there's actually a bigger issue at play. So we have that range of actual crater sizes, and we can sort of translate those back very roughly into impactor diameters and try to say for an impactor diameter that hits into Imspon's and into, or the Oriole and into the Planitia, what is the actual expected difference based off of what does this effective strength need to be to get what does the effective strength in the Olympus Mons Oriole need to be to have a base effective strength in the Amazonas Benicia? That's where we put it. And you get to actually the effective strength that you need in Olympus Mons Oriole varies over that whole possible range of impact or diameter distribution. And in every single scenario, even down to where the effective strength in the Amazonas Benicia is just sand, basically, very loose, very uncohesive sand at 0.1 mega or 0.01 megapascals. The effective strength in the Oriole at the largest impactor sizes crosses a hard rock limit of 10 megapascals, which pretty much at that point, you're not looking at rock, you're looking at something like steel. And does the landslide deposit on the left here look like steel? I do not think it does. So even though the difference here implies a strength difference could be possible, the actual physics, the math says that is very unlikely. I've heard I've talked to some folks about using and invoking landslide shielding, but not only would that shielding have to be very strong itself, where you have stronger rocks on top of weaker rocks as you sort of mix a landslide moving downwards. Not only would you need a stronger rock on top to be fine, then it would need to stay strong throughout all the weathering that the Olympus Mons Oriole had over the Amazonas Benicia, since it is a much older terrain. Okay, so strength isn't likely to be our answer here in this situation. For those of you who guessed porosity, you're maybe correct. So let's go and look at porosity and what the crater scaling equations say about that. So the Amazonas Benicia has the porosity in the range of 10 to 15%, which is pretty reasonable, especially over the first, if you average out first 10 to 100 meters or so. You get that the porosity in the Olympus Mons Oriole needs to be something like 48 to 68%, which is high. It's not unreasonably high, especially at the low end for very fluffy landslide deposit material, possibly made of. There are landslides on Earth made up of pyroclastic material that can have up to 50, 60% porosity within them. But then that's a very specific type of situation where you have very sort of particular materials and they're very limited in range and scale. Right. So to actually show what the results of the actual crater scaling equations look like in terms of porosity, so you get a bigger picture of what's going on, this heat map is what we get. And the right, so the this is a sort of contour map, and it is showing the dark line here is the 1.43 sort of factor, and plus or minus 0.11, which are these dashed lines, and we get our the 48% is somewhere down around here. So that's if the difference is smaller than what we're measuring, or the best possible what we're measuring, and the AP unit has a low porosity, it could have an even lower porosity, right? And so I want you to notice two things here about this plot. First is that as you start to push up the AP unit, the Amazonas Benicia porosity way up, you start to get really, really unphysical porosity going on. And as you push it down, there seems to be a minimum implied porosity from that actual factor that we get. Although I wouldn't take that too much I would take that with a grain of salt, actually. Because some other factors within the crater scaling equations will change as you push down. Regardless, I believe that this is a very unlikely. Well, I do think porosity is actually the factor at play here, causing that crater diameter difference. I do not believe that the actual porosity in the Olympus Mons Oriole could be 50, 60%. So there might be something wrong with the crater scaling equations within the sort of parameter range that you can apply to secondary impact events. They're going on the order of hundreds of meters per second rather than tens of kilometers per second compared to primary impact events. We're typically looking at smaller sizes. We're typically not looking at complete vaporization of the impact material, and so the actual current equations could be overly sensitive to porosity within sort of the secondary cratering regime. Regardless, I do think the actual qualitative difference at play here is porosity. It makes sense based off of the background geology. And it makes sense to some degree that the Mons Oriole is very porous. There's just very little wiggle room when you sort of work off of this. So my hope with this method, with this project, is that it kickstarts the creation of a crustal property difference relation web across Mars. So we got that porosity difference between those two areas. If you go and find a good, secondary cluster crossing over at some other point that crosses in Olympus Mons Oriole, you can then say something about that area the Oriole's touching and Olympus and Amazonas Planitia and how those two relate to each other. So I'm hoping that gets started by people who go through the opposite method of finding a cluster and being like, oh, look at that. Maybe we can learn something from this about our study area, and they go and they find this method. Or better yet, or maybe not better yet, but I think that would be really cool if this actual seeing that there's a qualitative difference between these two areas that needs to be further studied could drive actual exploration from missions towards interesting areas like that Amazonas Planitia, Olympus Mons Oriole contact. Yeah, and then past Mars, I have looked at this methodology, this concept on Mercury, on the Moon. The problem with those worlds is even though there's plenty of secondary craters, there's usually just a great patchwork of different primary craters that produce a whole bunch of different secondary craters, which is great if you can trace them back properly. But then the actual geologic differences aren't very sharp as compared to Mars. And the sort of diffuse boundaries, as well as sort of not there being very many boundaries, makes the actual finding a really good spot to do this pretty rare. And then thinking about bigger picture secondary cratering work, there's actually recently other secondary craters were recently found on Earth in Southeast Wyoming by Kinkman et al. I'm interested in learning about how to actually properly put field trip studies in with, or field work studies, excuse me. You'd all just love to take a field trip out there. Field work studies into proposals and perhaps looking at these sort of secondary craters and other possible secondary craters elsewhere on Earth to sort of look at them in terms of crater scaling, and are they matching what we expect when we actually go and look at them in higher detail. And then the last thing I want to actually go and study with secondary craters in the sort of concept, in this vein of looking at how secondary craters scale, is looking at Pluto secondaries on Europa. This is Pluto. It's one of the largest impact craters on Europa. There's a whole bunch of secondaries, as you can see from all these bright rays that come radiate away from the center crater. If we go up to here, just north of Pluto, to the Connemara chaos region of Europa, where there's possibly been some exchange between the surface and subsurface. You see that there's actually a ton of secondaries in Connemara chaos. So Pluto is actually younger than the majority of Connemara, which is interesting. It tells you something about possible time scales for chaos terrain formation. But we can actually go and look at the secondaries themselves, and we can see that there's at least one, I think there's a few different clusters of secondaries that have hit into boundaries between plate material and matrix material. And I'm finding that the plate material secondaries seem to be larger, which is interesting. And that might actually be a strength signal over, say, a porosity signal. but I need to go research that more, and I would prefer to actually get some funding to do so. All right, so that was what I wanted to say about secondary craters. I see I have like maybe 5-10 minutes left, so I'm going to very quickly go through the next 2 points, which is fine because I kind of planned for that anyways. So first I want to talk about lunar large impact structures and look at the actual thermal history of the moon through that context. This was one of the very first projects I worked on in Santa Cruz with Francis Nimmo. Thanks to the wonderful GRAIL gravity data, the crustal thickness maps derived from that data sort of show that there's a very interesting property of very large impact structures on the moon and other worlds, but very clearly seen in our really good lunar gravity data. And that's that impact structures above about 300 kilometers and definitely those above 450 kilometers in radius have thinned crust at the middle of their impact structures. And you can see it here with all these blue circles and some light blue circles around. And those are thinner. So beyond this, sort of also using this data, a group actually discovered that there were numerous impact structures that I've actually starred out here, although there's this one right here that were discovered using only gravity data, in that they have thin crust, but the surface topography has become muted over time because these structures are extremely old and have topographically relaxed due to impact diffusion, but also have relaxed due to inflow of the crust when they formed, because back when they formed, the lunar crust and the lunar mantle were a lot hotter than what they are at now. So using a relaxation proxy that Francis Shinichi Kamada and I developed. I would say developed, but it's pretty simple. We compared the actual crustal thickness on the interior of impact basins to the surrounding crustal thickness, and this is just the crustal thickness ratio. If this ratio is low, you are looking at an unrelaxed, relatively well-preserved initial impact event, or actual initial impact structure from when you form it. Otherwise, if it has had time to flow and relax away, your crustal thickness ratio is going to be a little closer to 1. And so the important thing that I found is by looking and getting relative age for the surfaces of these newly discovered areas, we do show that there is a correlation between the crustal thickness ratio and the sort of implied crater counting relative age, in all the impact structures on the moon, except for, of course, South Pole Aiken. When is that not an outlier? And what we found, is that there's really about 2 to 3 different groups, or it sort of decays away. And this actual difference between these crustal thickness ratios and these over here isn't just a timing history and the actual number of craters on the surface and thus the age of the surface, but it's also a difference in the thermal history. So we can link this sort of relaxation transition on the moon to an actual thermal models of the moon that look at how the moon has cooled, solidified from its lunar magma ocean state to and through to its modern day. And here's what we get when we actually plot up those two sort of time windows. In that we get, we see from that previous plot that there was a number of impacts after that relaxation transition. It's somewhere around 10 to 15. And we can see where that crosses over in terms of the thermal window for LMO closure and crustal cooling through the context of lunar impactor chronology models. So really the number of impact events as a function of time, because we're looking at the entire lunar surface here. In terms of lunar impact chronology models, there's really 2 flavors that they come in: those with a late heavy bombardment and those without. Those that do have a late heavy bombardment tend to, they have a sort of kink and their distributions around here. And that kink requires that they have a very flat, decay up until that sort of kink point to make the actual number of impactors that we see and derived understand on the lunar surface make sense. And thus they cross this window at an earlier point in lunar history, implying that in order for these late environment models to make sense, they have to be correlated with a fast cooling lunar magma ocean / crust in order to explain the actual relaxation that we see in terms of the number of events before and after. Whereas for a slow cooling lunar magma ocean and crust, you basically can't have a late environment as well. You need to have a monotonically decaying rate of impact events, at least at that crossover point. And so when scientists out there actually go and determine that, say, the actual lunar crustal thermal conductivity is much lower than we thought it was, the lunar magma ocean was really long-lived, and the crust itself took a really long time to cool off, that's actually saying something about the actual possible impactor chronologies based off the observations that we see. And I believe that there has to be some other observation out there that can further link these two, or maybe discount certain types of models and really force us towards looking at certain models and thinking about how, in light of future Artemis missions, do we need to update? Right. Right. Okay. I realize I'm probably running very short on time. As I take a drink of water. So I'm going to very, very quickly go through some what I call non-water channel morphology, and think about what the actual formation of channels seemingly formed by fluids on other worlds that seem to lack surface water. I'm mainly looking at canali on Venus and the rills on the moon. So canales on Venus really, I'm mainly just going to point you all towards a paper I had published last year that was looking at Baltus Vallis on Venus. Baltus Vallis is, I'm going to call it the longest non-continuous channel in the solar system. It's over 7,000 kilometers long if you start counting the parts where lava flows cover it up, and maybe it's a little hard to determine. However, if it formed as a surface channel, it probably likely had to follow the flow of gravity on the surface when it initially formed. And what we find is, through this analysis in the paper, that the topography, or the channel itself, does not conform to modern topography. Basically not at all, across pretty much all wavelengths of the channel. And that's really nice if you want to go and determine wavelengths of tectonic processes that have altered the surface of Venus, which I did. However, I want to expand looking at canali more, especially in light of Veritas getting refunded. Yay, very happy. And I want to go and look at how this sort of methodology changes, or not methodology change, but like the actual analysis varies based off of all the other canali that can be on the surface, because there are a lot of canali. These are sort of broad areas that have a whole bunch of these channel structures, though none of them are quite as long as Baltus Vallis. Will these shorter ones show a similar trend, or will they prove to be less altered or more altered, right? And looking at lunar rills in a similar way, we sort of have an opposite situation where the lunar surface is unlikely to have been altered since rill formation, at least on length scales that rills exist, in the hundreds of kilometers up to. However, what I found is that rills actually behave about as well as rivers on Earth compared to the background topography, that they flow generally downhill about as well as rivers on Earth do, up until about spherical harmonic degree 80. which is about 180 kilometers on the moon. Past that point, they don't really care whether or not they flowed up or downhill compared to the background topography, which is interesting. I think it's a signal of their actual formation process. However, this is something I'd love to actually talk and have meetings with more senior PSI scientists and learn how to develop a really good, really interesting research question off of this observation right here. All right, so I'm going to leave up my future lines of research. These are sort of the big questions that are, at least ideas that I want to sort of go after in regards to proposals. I talked about the first three. The last one is sort of rose out of some conversations and talks I watched at HQ where, the Europa Clipper is going to get really good gravity of the actual subsurface ocean floor topography. And I think a lot of the evidence and a lot of very starting math that I've done shows that it might be really hard to make actual morphology on the subsurface ocean floor. So right, I'd be interested in working towards an idea in that line too. And this is where I'm going to leave it. Thank you very much for having me give a talk. I would love to answer some questions. Thank you.
Thank you very much, Jack. Very, very, very interesting. I've got some questions, but does anybody else have questions right now?
Yeah.
Go ahead and chime in.
Hi, I do have a question. I'm not a geologist, but going back to the secondary crater counting. So what about differences inside the region you choose?
Yes. So in the region, so you're talking about variations internal to the cluster or variations in the geology itself?
Yeah.
Okay. Yeah, so there definitely are variations within a cluster. You can get like denser spots and less dense spots. The hope is that by making our counting areas pretty large as we can reasonably make them such that they are still within the cluster, but capture similar variations on either side of the boundary. We sort of hope to get around that through volume.
Okay.
Yeah.
Thanks.
And you'd probably be able to see it in the actual cumulus size frequency distributions, the actual distributions of the craters. You can imagine you would see a really tight cluster of in one rather than the other, but we don't really see that, at least in this area that we looked at.
Jack, my question is, I was taken by your last line of your last slide about ocean or ocean surface or
yeah, it's such a hard we need some sort of like other term for the rocky
or
floor, yeah.
But we're gaining physical oceanographers at PSI, and it seems to me that yes, because there's overlap, and certainly currents might affect the topography of an ocean floor, and so and we have people that are modeling currents and turbulence and stuff in the Earth's oceans, and it will be interesting to see how some of those models might translate, at least in a theoretical sense, to Europa, Enceladus, and things like that. And so these are some people you might reach out to, and with the idea of adding that, those kinds of considerations to understanding what might be observed down there. At the same time, I was speaking to another physical oceanographer a month or so ago that was interested in joining us, and she'd just written a paper on the production of waves on ocean surfaces from winds, And so we were talking about how that might apply to Titan. So
Ooh, yeah.
so this is all good stuff. So yeah, things like Europa really open up some broader questions.
The question, I put it in the chat.
Oh, so yeah, Megan Russell, you asked a question. I'll be glad to read it out first. So how much hotter was the lunar mantle and surface when those now relaxed craters formed? Is it possible the same mechanism operated on Venus that can explain the relative lack of craters? Yes. Well, okay, so the first question is the sort of, because viscosity is so temperature dependent, the sort of crossover temperature point is at 1400 Kelvin at the mantle crustal interbase. So yeah, it happened pretty early. I'm unsure if Venus is that hot, but I think it's more of it is close enough in hotness and possibly some mechanism to erase large craters, certainly.
Cool, yeah.
You sort of, you make a trade-off between temperature and time.
Yeah, exactly.
Yeah.
And
Yeah.
I know there's a Nemo and Macwell paper out looking at the large tessera provinces in 2022, I think it was, to look at the relaxation. And I can't remember what they said about that, but they were looking at very large, broad regions.
Yeah, I know exactly what you're talking about. I'm trying to think of it. But yeah, I think it's a similar thing where it's just like if you have a crustal root that's too big, which I guess sort of the inverse can happen with craters. Yeah, it just gets too hot and mushy and yeah.
Yeah.
Right.
Cool.
Yeah. Cool.
Nolan, you got a question?
Yes. This is actually somewhat related to the very first question asked. The ejecta, which caused these secondary craters, as a function of the distance from the primary crater, say X versus 2X or 3X, are there differences in the size distribution or the velocity distribution?
Yeah, so this isn't my work. You should look up a great scientist by the name of Kelsey Singer. She's looked at the radial dependence. And when I do that sort of analysis within my counts, I'm just doing it to make sure there's no dependence within my my 10-kilometer range I'm looking at.
Okay.
Yeah, so that my ranges are a bit short to see that dependence, but there is some good work about that, and it's a very it sort of sets a watch out zone within like the first 50 kilometers or so from these sort of larger complex crater size craters, where your velocity is just your impact velocity decreases rapidly. Or actually, no, it increases rapidly because you actually need a lot more velocity to get farther, right? Yeah.
Mm-hmm.
But the actual size of the impact crater, so the actual energy involved is a lot higher earlier on, and so that varies very quickly.
Thank you. So basically what you're saying is it should not affect your analysis.
No, my analysis is affected by that. Although I do calculate it because I need I need to make sure that it's doesn't vary too much within my accounts or my ranges.
Okay.
Yeah.
Thank you.